Hey Black Hat, it's great to be here with all of you and to be part of this event. Today we will talk about SBOMs, software bills of materials, and some of the challenges we faced in creating them that led us to develop Surfactant, a modular framework for extracting information from files, with the primary goal being to generate file-level SBOMs that contain accurate information and relationships between the files that make up a software system. And it is open source. So after the talk and demo, you can go to our GitHub repo, linked below, install Surfactant, and use it to extract information from files. Before we dive in, let me introduce myself. My name is Ryan Mast, and I'm a cybersecurity software engineer at Lawrence Livermore National Laboratory, where I work on various projects related to energy sector security that can involve some mix of software development, vulnerability research, and firmware analysis. It is part of one of these projects that we developed Surfactant and use on a regular basis to create SBOMs. If you want to reach out with any questions or comments after the event, you can find me on social media at rmast, on GitHub, or you can reach me via email at mast9@lnl.gov. Now, some of you might have never heard the term or not really know what it means, and be wondering, what is an SBOM, or software bill of materials? In short, an SBOM is like a nutrition facts label with details on what makes up a piece of software. For individual files, it will have basic information like the file size, type, and hashes. It may also contain a product name, vendor, and version information. At a more detailed level, it may try to capture information on what statically linked or header-only libraries make up a binary, as well as capture dependencies on other files or packages on a system in order to establish relationships between them. From a practical standpoint, the information captured will depend on who created the SBOM and what they intended to use it for. Generally, there are two levels of detail that a user might care about in an SBOM. There's file-level SBOMs, where you try to capture information about every single file on a system and the relationships between files, for example, one executable using a shared library. This kind of detail could be really useful for a security analyst or someone doing incident response who wants to determine if a vulnerability actually applies to a system. On the other hand, if the SBOM is generated without access to source code or a package manager metadata, then you may not know what a file is. For example, you might not know that a file is part of a well-known package such as OpenSSL, and you might not even know if that file contains compiled code or just arbitrary data. There are also package-level SBOMs that try to capture what packages and their versions are present on a system. This can be useful for consumers to evaluate the risk of buying a product or to determine if a CVE may affect them. It can also be useful for vendors in tracking which components they still need to update. The biggest downside we've noticed with this is that oftentimes the SBOMs we receive from vendors, which were probably generated from source code or package manager data, do not show any information on how the packages relate to one another, nor do they have any information on the files on an actual device. If you ask for an SBOM, then you'll probably get a JSON file, or maybe a tag value or YAML file, that meets one of two main specifications. SPDX is the older one from the Linux Foundation, and it was aimed more at license compliance. The other format, CycloneDX, is from OWASP, and it's a newer format that came out in 2017 that is aimed at cyber risk reduction and supports extensions that can be useful for conveying security-related information. Now that we're on the same page with what an SBOM is, here are the challenges we face that led us to develop Surfactant. First off, we typically receive compiled binaries from the vendors we work with, but we do not get access to source code. This often consists of Windows PE files that target the .NET runtime, as well as MSI installers. We will also get structured firmware for Linux or VxWorks operating systems that have a file system with many files and limited or no package manager information. We will often run into custom file types that we need to be able to add support for, as well as being able to output gathered information in a custom output format. We looked at open source tools, but they tend to focus on package level information and have limited support for C and C++ binaries and firmware. The same is true for commercial offerings, which have limited support for firmware, and we do not have any real ability to add features to them ourselves. The inspiration that led to creating the first version of Surfactant was that if you right-click on a file in Windows, select Properties and then Details, you can get a bunch of interesting metadata like the product name, product version, and a copyright string that often identifies who made a piece of software. Similarly, macOS you can select Get Info on a file and see some version information and a copyright string. So, why not leverage all the interesting metadata that different file formats have to create an initial starting SBOM, and then use manual analysis and other tools to add package level data and statically linked library information to the SBOM. So with that background information, let's take a deeper look at what Surfactant is and what we mean when we say that it is a modular framework. To start off, you give Surfactant either a directory or more commonly a configuration file that is able to list multiple directories alongside supplemental information you provide it to help establish accurate relationships later on. From there, Surfactant traverses all of the provided directories, and for each file it tries to identify the file type. For recognized file types, it will then try to pull out additional information that can be useful for identifying what package the file belongs to, what the relationship that file has with other files is, and information that could generally be useful to a security analyst in the future in determining what vulnerabilities might apply to the system. After finishing gathering information, Surfactant then moves on to a sort of analysis stage that is primarily used to establish relationships between files based on the gathered data. One of the key points here is that we try to avoid making inaccurate guesses that would introduce wrong information into the SBOM. So as an example, let's say you have an application that uses dependency A. The naive approach to establishing a relationship would be saying, okay, which of the files that we've seen have a name that matches dependency A? The problem is, if you have multiple files with the same name that are used by different applications, then you have no idea if the relationship you've created is to the correct dependency A file. So our solution to this problem is to emulate how the operating system or runtime environment would determine what file to load for a dependency. So let's say that we're using .NET. We will internally construct a list of probing directories as closely as possible to what the .NET runtime environment would do, and then limit our search for dependency A to those identified probing directories. Finally, we write the information out to a file. By default, this is a custom format that includes all the information we have. However, we also support outputting a limited subset of the information to CSV, SPDX, and CycloneDX files. Ideally, we'd like to be able to output all of the information to CycloneDX by leveraging CycloneDX extensions. However, this feature is currently a work in progress. Now, as for the modular aspects of Surfactant, all the core functionality is implemented using the same set of hooks that is available to third-party plugins. This includes identifying file types, extracting information from the files, analyzing gathered metadata, and writing output files. You should not need to modify Surfactant source code in order to extend its functionality. For example, if you want to output a .graphis file, you should be able to write an output format plugin that does that. If you want to create a file extraction plugin that pulls files out of a tar archive and then tells Surfactant to gather information from that newly created folder, you should be able to do that. So, enough talk. Let's see what this looks like in practice with a demo of how to use Surfactant. To start off, here's a quick look at the GitHub repository. If we scroll down, then you can find some basic installation and usage information for Surfactant. You can also find a link to the documentation that will take you to the Read the Docs site, which has a bit more detailed information on the topics covered in the README. The first step for installing Surfactant is to create a Python virtual environment. This helps ensure that any dependencies Surfactant has will not conflict with dependencies that other software on your system uses. After that, just pip install Surfactant in the virtual environment, and then a little bit later you should have Surfactant installed. One thing to note though is that the PyPI package tends to lag behind in features compared to the current development version of Surfactant on GitHub. If you'd like the latest features, then git clone the Surfactant repository from llnl/surfactant on GitHub, and after the repository is cloned, then cd into the cloned repository, and do a pip install from that directory. This will give you the absolute latest features that may not have made it into the PyPI package yet. After installation, Surfactant can be run from any directory. Providing the help option or no options will print usage information, which will show you options available as well as subcommands that you can use. This demo will focus on the generate subcommand. However, you might also find the merge subcommand interesting to look at. If we print out the usage information for the generate subcommand, we can see what arguments it expects. So it expects a configuration file or input directory, as well as an output SBOM file name. Additionally, you can see some of the options that it will take, such as a recorded institution for controlling what organization to put in the SBOM as its creator, an output format option which can control what the output SBOM format will be, and a list output formats option for showing what the available output formats are. Now, let's download a sample file to try running Surfactant on. For this demo, we'll use precompiled Linux binaries from another open source project, Helix. After the download finishes, we can unpack the archive by simply running the tar command on it. Often, this will be a more involved process that requires running tools such as unblob or binwalk to get the files out of the archive. For Windows installers, we found that using a Windows VM alongside sysinternal's process monitor is the best way to make sure that we get all of the files that were written from the installer, as well as the install paths they were written to. While at this point we could just give Surfactant generate the directory that the files were extracted to, this won't have accurate information on relationships in the SBOM. For that, we want to create a JSON configuration file with some more details to help Surfactant out. The structure of this file is a list of JSON objects, each of which must have an extract paths key that has a list of directories Surfactant should traverse and gather file information from. These paths can either be absolute paths, or they can be relative paths to the directory that Surfactant is being run from. In addition, you can provide an archive key that is a path to an archive or install file that the contents of the extract paths came from. This will make Surfactant create a software entry in the SBOM for the archive or installer, as well as create contains relationships between that archive software entry and all the files from the extract paths. In addition to this, you can give an install prefix key, which tells Surfactant that the files under the extract paths would normally be installed under a particular directory on an actual system. So specifying / as the install prefix would mean the files go under the root directory of the file system. Specifying /user would indicate that the files in the extract paths would be installed under the /user directory on the system. We can now save this configuration file and then run the Surfactant generate command, giving it as a first argument this JSON configuration file we created, and as a second argument the name of the file to write the SBOM to. And we run it and see, oops, there's a JSON decode error, so let's open it up real quick and see what the error is. An extra closing square bracket. Let's just delete that real quick and then try running Surfactant again. And this time we see log messages indicating success. So now, let's take a look at the contents of this SBOM. Remember, we didn't specify a format, so the default was used, which is a custom format that has all of the gathered information. You'll first notice that there's systems and hardware entries that are empty, but then the software section is a list of entries for the files that Surfactant recognized. Each of these entries has a bunch of information, including a unique ID for identifying that entry, as well as a file name, which is the first one corresponds to the archive that we gave Surfactant. And then you'll notice the install path and container paths are empty because it's not within anything and not installed on a system. And then if we go farther down, you'll see that the next entry is one of the files from within the archive, libzrmq. So the install path is as if the file was installed under the /user directory, which we gave as the install prefix, and the container path makes it look like it's located under the UEID for the parent archive container under some directory structure. Now you can see that the metadata section has a bunch of gather information that's used for establishing relationships, as well as stuff that might be interesting to an analyst comparing SBOMs or looking in the SBOM to get some sense of what's on a system. If we jump farther down in the SBOM, there's a relationships list, which is a bunch of objects saying XUID relationship to YUID. So you'll notice the XUID for a bunch of the contains ones is for the archive file, and then the YUID would be for the individual software entries. Go farther down to the users relationship. Let's look up what the XUID corresponds to for this first one. And we'll do a quick search, and we can see that this corresponds to libhelix.so. So now, let's go back down to that users relationship again, and search for the YUID. Now, you can see that it's used by a few other binaries as well, and then we get up to the software entry for it, and we can see that is libzerumq. So this tells us that libhelix is using libzerumq, and since there are multiple relationships that have that same YUID for libzerumq, we know there's other files that also use that same shared library. Let's shift gears a little bit now and look at installing and activating plugins in Surfactant. So if the plugin is on PyPI, you can simply pip install it by name. If it's in a Git repository, then you can pip install directly from a Git repository, and if needed, you can specify the hashtag subdirectory option to say what subfolder within the Git repository the plugin is in. If you have a local Git cloner repository, you can simply pip install from that local directory as well. Once installed, the plugin will automatically be activated, and you can simply rerun surfactant generate to create an update SBOM with any information that the plugin gathers. So if we open up the SBOM now, after installing the fuzzy hashes plugin, we can see that there is now a TLSH entry in the metadata section of the SBOM with a fuzzy hash for every file. To wrap up the demo, let's take a quick look at how you write a plugin. We'll use the fuzzy hashes plugin as an example. So in the GitHub repository, let's go over there, and you can see it's basically just a pyproject.toml file and a Python file, making it a valid pip installable wheel. So if we open up the pyproject.tom file, it's just the typical metadata you'd usually see, along with information on the dependencies that need to be installed. And sort of the key point is it should have a surfactant entry point that is what enables Surfactant to automatically discover the plugin. If we then jump over to the Python file, you can see it's a relatively simple implementation. Again, the key point is it imports Surfactant plugin and then implements a function that has the Surfactant plugin hook impl decorator sort of applied to it in order to expose a hook that Surfactant will recognize. Currently, the most up-to-date source of hooks that can be used are in the hookspecs.py file, which has a number of functions decorated with the hookspec decorator. These include an identify file type, extract file info, establish relationships, as well as write SBOM, read SBOM, and a short name hook that can be used to give an alias to a plugin that implements another type of hook. Alright, so by now you've heard quite a bit of what Surfactant can currently do, as well as seen it in action. Here's a snapshot of what's next. First, we'd like to handle more file types, especially scripts in the Node.js and Python ecosystems. We also want to go beyond just getting file level details and incorporate more package level information in the SBOMs. Two of the ways we want to do this are if there's package manager files present, then we want to extract information from those to include in the SBOM. And in the absence of package manager files, we have some ideas that we're exploring for how to determine what package a file is part of based on the gather information. We have some ideas as well for output format plugins that could be useful for an analyst to visualize the contents of a file system, doing something like file system cartography. And finally, we have a lot of ideas for plugins that we'd like to implement, and we want to keep adding features that will empower plugin developers to do more. As some next steps, you can find additional information in the GitHub repository, so go check it out, read the docs, and share or star it. We'd also like to invite you to try things out, play around with Surfactant, and then open issues or discussions for any bugs, feedback, or ideas you have. Pull requests with changes are also welcome, and if you're at a plugin, we would love to hear about it. Feel free to reach out on social media or via email with any questions you have. And finally, thank you for being here. I hope you have a wonderful time at Black Hat.